Hello and welcome to our AP Physics 1 Project 3 Work Energy and Momentum exam answer key. We're going to start with question number 1, which says a ball of mass 1 kilogram initially at rest acquires a speed of 4 meters per second immediately after being kicked by a force of strength 20 newtons. For how long did this force act on the ball? So the impulse, which is delivered to the ball, can be represented by J equals F delta T, where J is the impulse, F is force, and multiplied by the change in time. And this equals the change in momentum. So since the ball started at rest, we have F delta T equals mv, mass times velocity. Therefore, change in time equals mass times velocity divided by the force. And since we have all these values, you can just plug them in. 1 kilogram times 4 meters per second, so velocity, all divided by 20 newtons. This comes out to be 4 over 20, which equals 0.2 seconds. And that is our answer. Therefore, correct choice is answer choice B. Okay. Is that okay or should I redo it?
Yeah, that was good. That was great. Alright, on to the next question.
Alright.
Yo, I like your teacher voice, man. You make a good teacher, bro. Nah, genuinely. Just, you don't have to click. No, just go next, click the arrow at the top. You see?
Oh, right.
Yeah, boom, number 2. Let's get to it.
2. So. Oh, wait, I gotta.
Wait, no, I got you. I can. Hold on. Let me intervene really quick.
Gotta write that.
Hold on. You don't gotta copy and paste the question. I can do something really quick to help you. Hold on. Boom. There you go. And. Oh, there you go. Second.
Okay.
Number 2. An object of mass m is traveling at a constant speed v in a circular path of radius r. How much work is done by the centripetal force during 1/4 of a revolution? Now, we can start with the equation F equals mv squared over r, which gives us the centripetal force. And we know that work is given by force times displacement, force times distance. And distance is given by...
You mean displacement, you're right.
Oh, displacement.
Displacement.
Damn it. Okay, I'll just edit.
No, that's fine. You can keep going. It's all right.
Yeah, I'm trying to think what...
Yeah.
Like, what was the last thing I said that doesn't need to be edited out?
No, it's good. We can keep all of this in, or we can edit it. Just keep going. You know, it doesn't have to be perfect. Mr. Iqbal understands, man.
Love Mr. Iqbal. He's awesome.
Yeah, like if you mess up, I'm here to catch you. If I mess up, you're here for me, man.
So normally the distance would be equal to 2 pi r, but since we're only looking for... I messed up. No, I actually have to restart. All right. I'm gonna erase this.
That guy's amazing, man.
Oh my god.
Is there a eraser option where you just erase by stroke instead of Let me see.
It shows whatever. Number 2, an object of mass m is traveling at constant speed v in a circular path of radius r. How much work is done by the centripetal force during 1/4 of a revolution? So we can start with the equation for centripetal force, which is F equals mv squared over r. We know that work is given by force times displacement, or FD, and the distance normally would be given by d equals 2 pi r, but since we're only trying to solve for 1/4 of a revolution, we need half pi r, because 2 over 4 is 1/2. So then we're left with, since we know work is force times displacement, and force times displacement equals mv squared over r times, oh, sorry,
You can control Z to undo.
times half pi r. This gives us 1/2 pi m b squared, which is our answer. Therefore, answer choice A is correct. Okay. You're right, Jamboard is pretty convenient for this.
Yeah.
Wait.
What's up?
Wait, hold up. Number 3. A student swings a ball around his head in a perfectly circular horizontal orbit with a constant tension. Which of the following is true concerning the ball's orbit? Now, the best way to approach a problem like this is to just go through the answer choices and process of elimination. There could be multiple right answers. Answer choice A says the ball's speed increases due to work done by the force of tension. Now, we know that the, so let's draw a little diagram here. So we know that the ball is not moving vertically whatsoever. It is only moving horizontally. Now the tension force, the tension force is only acting vertically. So there's no way that the vertical tension force could affect the work done by the force of tension could affect the ball's speed, since they're perpendicular to each other and they have no shared components or no components in the same direction. So answer choice A is incorrect. Answer choice B says no work is done by tension since it is perpendicular to the ball's path of motion. That's true. That's what we just discussed. Since they share no components in the x or y direction, no work is done by the tension force. So B is correct. Answer choice C says the ball maintains a constant speed. So we know that the tension is constant. So the ball, the force acting on the ball is not changing at all. However, the ball is constantly changing direction. So although the ball may have a constant speed, it does not have a constant velocity, which means that answer choice C is also correct, but answer choice D is not. Okay, that was kind of... In a billiards game, one player hits the cue ball toward another ball. The cue ball has a mass of 0.1 kilograms and hits the other ball with a velocity of 2 meters per second. If the collision is completely elastic and the cue ball travels with a velocity of 0.8 meters per second after the collision, what is the mass and velocity of the other ball? So 2 important equations that we are going to need to use here are the conservation of momentum and the conservation of energy, which are m1 vi equals m1 vf plus m2 v2 and 1/2 m1 vi squared equals 1/2 m1 vf f squared plus 1/2 m2 v2 squared, respectively. So we're trying to solve for m2, which is the other ball in this case, and v2. So we're going to use both of these equations to solve for them. We're going to use the first one for mass and the second for velocity. Okay. So here we would want to start with, well, let's take a look at the first equation. If we rearrange it, we get m2 equals m1 times vi minus vf. Kano recordam sa vtedy mio pote vf all over v2. Now v2 is a value we don't have yet, and we can get it by manipulating the second equation and solving for it. So we have to put this to the side for now, and we'll start working with the second equation. Now, in order to isolate v2 squared, to avoid all the busy work, I'll just skip straight to it. So v2 squared equals m1 times vi plus vf times vi minus vf all over m2. Now we substitute our equation for m2 into the denominator since we don't have the actual value for m2 yet. So we can just erase m2 and plug in the expression, which is m1 times vi minus vf over v2. Now, if we rearrange this yet again, we get that v2 squared is equal to m1 times vi minus vf times vi plus vf over m1 times vi minus vf times v2 raised to the negative first power, since we got rid of that double fraction we had in the denominator. And this, we can cancel out the vi minus vf's and the m1's, and we're left with, actually, I'm just going to bring this up there. We are left with vi plus vf over v2 to the negative first. Now we can just bring this to the numerator since it's raised to the negative first power. So this just equals v2 times vi plus vf And since this is all equal to v2 squared, we can divide each side by v2, and we're left with v2 equals vi plus vf. That's pretty neat, nice and simple. Which, since we have vi and vf, is equal to 2 meters per second plus 0.8 meters per second, yielding 2.8 meters per second. Now this is only the first part of the problem, but since there's only one answer choice where 2.8 meters per second is the velocity, we can assume for now that the correct answer is choice B, but just to make sure, we're going to solve for M2 as well. And just plugging everything into the equation we got earlier, M2 equals 0.1 kilograms times Vi minus Vf, which is 2 meters per second, minus 0.8 meters per second, over V2, which we just derived, which is 2.8 meters per second. And this should come out to approximately 0.043 kilograms, which checks out. Therefore, the correct choice is answer choice B. Here's the crate sliding down the plane, and this is height H, length L. And since we know that the crate falls down a vertical distance of H, and we know that gravitational potential energy is represented by mgh, the gravitational potential energy of the crate would decrease by mgh. The length of the ramp is just completely irrelevant in this question. However, if friction were involved, then the length would matter. But yeah, and since it's going down, its gravitational potential energy would change by negative mgh. Therefore, correct answer is choice A.
Oh.
Number 6, So, 2 frictionless carts weighing 300 grams each are at rest on a level surface. A student taps the release so that one cart pushes off the other. If one of the carts has a speed of 4 meters per second, what is the final momentum of the system in kilograms times meters per second? So the 2 carts are initially at rest. Therefore, the initial momentum is 0. And if conservation of momentum holds true, the final momentum must also be 0. Therefore, the numbers are just there to trip you up, and the correct choice is answer choice D. Since there is no momentum initially, there is no momentum in the end. Nice. Which of the following most accurately describes a perfectly inelastic collision unaffected by external forces? A. Total linear momentum is conserved sometimes. Now we know that this is not true. This is a principle of physics. B. Kinetic energy is never conserved. Now this is a true statement. In a perfectly inelastic collision, kinetic energy is never conserved. Now, some of the initial kinetic energy is always lost to heat, and some is converted to potential energy in the deformed shapes of the objects as they lock together at the moment where they collide. But yeah, kinetic. Yeah, that's the reason why kinetic energy is never conserved. So we know B is true. Kinetic energy is always conserved. Well, we just found out that that's not true. And total linear momentum is never conserved. It's also not true. It's a basic principle of momentum. Therefore, there's only one correct answer choice to question 7, and that is answer choice B.
Let's see. Mr. Iqbal is hired to test the crash safetiness of the new Tesla model when it collides into a wall. Mr. Iqbal wants to know which of the following scenarios is most indicative of the least amount of force employed onto the Tesla. Employed, oh boy, employed, another word for exerted. So we want to know which scenario does the car have the least amount of force exerted upon it. So let's go through each of them. A, the Tesla crashes into the wall and yeets backwards. So in a scenario like this, we would draw out a car. That's our car. And then say it has an initial velocity going into a wall. And then the final, this is the momentum before. Momentum we know to be mass times velocity. And this is the velocity going towards this way. And then in the scenario after, it says it crashes into the wall and yeets backwards. So the car would then be going this way with a velocity of this away from the wall. And then this is the momentum before P initial. Momentum after would be P final, and it would be mass times this new velocity, right? And then the change in momentum would be, well, it would be a great change because the momentum initial has a velocity going this way. Since the mass stays the same, of course, the only thing we should worry about is the velocity. Since velocity is going this way, for it to change into a velocity going this way, it has to be a great change. And the significance of this is, let me erase this real quick. Oh, I should probably explain the significance of the, so there's the, hold on, exerted. So the, not force, the impulse momentum theorem, yeah. So the impulse momentum theorem tells us that force is equal to the change in momentum, which is impulse, over the change in time. All right, I'm gonna do a quick derivation of this. So we know, what was it? Newton's second law is force equals ma, mass times acceleration. Acceleration is change in time. I mean, change in velocity, my bad, over change in time. And then we can multiply change of time over here. So it's force times change of time. We know force times change of time to be oh shoot, what's force times change? What was this again? Power.
I muted myself.
Not important anyway. Man, I'm pretty sure this is. Wait, we can cut this out to power video editing. Oh yes, force times change of time. Force times change of time, of course, is power. So P. Sorry about that. P. Wait, no. Oh, hold on, no, something else. Oh, no. Scratch. Ooh, okay. So now so we have force is equal to change of velocity over change in time. We know mass times change of velocity. Mass times velocity is momentum, so we just have change of momentum over the change in time. That's how we get the derivation for this thing. Impulse equation formula. Yeah. Yeah. Hold on. Oh my god. So when we multiply change in time to this side, force times change in time, of course, this is impulse, and this over here is just what's that change of velocity? This is change of momentum, which goes to change in we did denote momentum as P. I don't know why. Force times change in time is impulse, we denote as J, I believe. So impulse is equal to change of momentum, basically. Okay, that's nice to know. Where's the eraser? Anyway, that's just quick derivation. Not important to, I mean, kind of important to answering this question. I just leave it like that. So back to what I was saying about the change in momentum of the car or the Tesla when it crashes into the wall and goes in a different or opposite velocity direction. That would mean it would have a great change of momentum, which is delta p. And then if you have a large number for the larger the number of numerator would mean the larger number of this final product's quotient, whatever. So if change of momentum is goes up, the force goes up too. So that would not give us the least amount of force, which is what we were looking for. All right, so this is just not it. B, Tesla explodes and leaves no remains. So in order for the Tesla to explode, you would need a lot of force. So this is, yeah. See, the Tesla sends a test dummy flying out the car. This tells us nothing about the force exerted upon the car, but tells us artificial information about the dummy, which we do not care about. And the process of elimination, D is the right answer. But another explanation as to why D is the right answer is when the car crashes, right? What happens when a car? So you know how a car has this like I forgot the technical terms like suspension something, where the reason why cars are constructed designed like this is because there's that crushing force into a wall basically. Takes a lot. Wait, what? It takes a long amount of no? A great amount of time, right? And then what we know from this equation right here, oh boy, is that if time goes up, right? If the denominator goes up, the ultimate, I don't know what to call this product quotient goes down. So if change of time goes up, the longer it takes for this momentum or force to be exerted, right? Not momentum. The longer it takes the time for this force to be exerted, the force is actually going to be weaker, right? So if it takes, say like, for I don't know, 100 seconds or whatever, for this car to crash, then the force will be less. You can tell from this equation. The number goes up, this goes down. I took a little too long to explain something that's conceptual and easy, but yeah, that's it. All right, number 9.
Why
Huh?
did you spend this much time?
I'm sorry.
Nah, chill.
Eddie rides a minecart in a mine shaft that has a massive.
Oh, no, chill. I'm the one sharing the screen. I gotta be on slide 9. Wait. All right, go.
You got a what?
Because they can only see my screen. They can't see your screen.
Oh, well, Eddie rides a minecart. Number 8. Eddie rides a minecart in a mine shaft that has a mass of like 5.
Number 9, by the way.
Oh, what did I say? Number 8. My bad. I meant number 9. Sorry. Kinetic energy of Eddie's minecart is roughly 8 joules. Eddie ends up colliding into Emmanuel's 10 kilogram car. Ooh, he got a 10 kilogram car. Headed directly towards him with a roughly 10 joules of kinetic energy. An onlooker of this unfortunate minecart crash incident wonders what the kinetic energy of the system is after this colossal collision. So this question right here is asking about. So in this collision, kinetic energy is conserved. I'll just draw a quick little diagram. So we have Eddie's cart. This is Eddie's cart. 5 kgs going this way. Got Emmanuel going this way with what was it? 10 kg. Sorry, 10 kg. Eddie's car has kinetic energy of 8 joules. Emmanuel's car has kinetic energy of 10 joules. So, going to this collision, right? Since kinetic energy is conserved, since it is a elastic collision, the change in kinetic energy will be 0. What do we know about the change or delta kinetic energy? Delta kinetic energy is equal to kinetic energy final minus kinetic energy initial equal to 0. What is it getting? Let's see. We can just move initial to the side, so it's just going to be KE final is equal to KE initial. All right, and then this is getting really messy, man. So we have the kinetic for turns out we don't know kinetic energy final, of course. We have kinetic energy initial for both of them. So kinetic energy initial is the I'm just going to drop down to kinetic energy final. I don't feel like rewriting it. Sorry. So kinetic energy initial, we have this card, which is Eddie's card, 8 joules. Just drop down 8 joules. So this is 8 joules. Wait, hold on. Sorry about that. I'm just gonna 8 joules plus, can I write? Oh, no, we can't for shoot. Get 8 joules plus this is the manual's card 10 joules, right? And then what we got here is we got to find out what the kinetic energy final is. What am I thinking? Is it back? Oh boy, it's back. So 8 plus 10, that gives you 18 joules, tells us the kinetic energy final is 18 joules. And we want to know what the kinetic energy system is after cross collision. 18 right here, 81, 9, and 1.8. I don't know how you get that. 18 is the correct answer. I think I'm gonna stop drawing. It's taking a lot of space. Mr. Iqbal tests out Ferraris in his free time. Wow. And is driving one with a mass of 1,000 kilograms. 1,000 kilo. I need to get used to riding with a mouse. So mass equals 1,000 kg. Velocity of 11 meters per second. That's going to be helpful. We should know that. 11 meters per second. Oh boy. Where did my mouse go? I lost my mouse. Hold on. Alright, I'm back. He collides into a solid wall and Ferrari goes complete to rest. So this is V initial, sorry, and this is V final, which they told us it goes to rest. Meters per second. Goes to rest. Oh, that's great. It tells us time within 2 seconds. T equals 2 seconds. Mr. Iqbal wants to know what is the force that just acted upon the car. All right. So how do we do this? Well, we solve this using impulse, of course. We know impulse, which is divided by J, is equals to force times change in time. And then we also know that by the force, not force, the impulse momentum theory, that impulse is actually equal to the change in momentum, which is delta P. All right, using this information, we can mess around with the equation, right? So you just F delta T is equal to delta P, and then you can end up with force, since the question is asking for the force. Force is equal to change in a minute, change in, move this over, yeah, change delta P over delta T, almost reverse that for a second there. All right, and then now that we have this equation, we can change, we can elaborate on delta P to be for, rewrite it. Delta P is P final minus P initial. Sorry, poor handwriting. Bottom is delta T. Then time 2 seconds, delta T also 2 seconds. We can start subbing in whatever we got. Oh yeah, I should probably elaborate. We know momentum P is actually equal to mass times velocity. Then is equal to mass times velocity. So we have mass initial times velocity. Mass final. Sorry, mass final times velocity final minus mass initial. This is getting hard, right? Velocity initial all over delta T. Delta T we know is 2, so just put 2. Why not? And then we can start by, well, V final 0. Everything goes to 0. Wait, sorry, not that. Just this. And then we can rewrite as, I'm just gonna skip that and just put it equal negative M1 V1 over delta T, which is 2, which I already put here. M1 we know 1K, so let's put 1K. Yo, Emmanuel, how did you get used to writing with a mouse? It's so hard. 1,000
I'm gonna get lazy.
Okay. Times 11 meters per second, all over 2, of course. If you do the algebra, 1,000 times 11 divided by 2 gives us, all right, go all the way here. Gives us negative 5,500 newtons. This is kg, this is meter per second, this is seconds. This is 5,500 newtons, which is this, and it's negative. All right. Mac is in a AP Physics 1 class and encounters this misconceptual question and needs help figuring out. The question asks, if you're rock climbing and the time it takes you to climb up the cliff goes down significantly, what happens to the quantity of work done by you against gravity? Help Jack answer this question. What is the conceptual question? So the quantity, all right, so what we know about work? Well, work is equal to the dot product of force and displacement. Yeah, that's the formula for work, right? And then what we know is that you are rock climbing. The time, cubic time takes you to climb up the cliff goes down significantly. So say we have, I don't know, like a cliff here, and you're rock climbing. This is you, you're rock climbing, and then time for it takes you to go up the cliff goes down significantly. Well, time has no place in this equation in deciding the determining work. So what happens to quantity of work? It remains the same. Nothing happens to it. Quantity of work done by gravity increases? Nope. Decreases? Nope. Alternates between increases and decreases? I don't even know how that happens. The answer is A. Next. Oh, Ethan is messing around with a spring for no apparent reason. Ethan finds out that the spring he is playing with has a mass of 300 grams. Oh, Ethan pulls out a Rubik's Cube from his pocket. I don't know why he has a Rubik's Cube in his pocket. That has a mass of 0.3 kilograms. Well, 300 grams and 0.3 kilograms are the same. They're like the same mass. And he decides to rest the Rubik's Cube upon the spring and press it down by vertical displacement or compress it by vertical displacement of 0.4 decimeters. 0.4 decimeters should be, do some mental math real quick. Never mind, a lot of bad at mental math. I need a 0.4 decimeters to meters. 0.4 decimeters is 0.04 meters. Yeah. So vertical displacement is 0.04 meters. Spring has a spring constant of 2,000 newtons per meter. 2,000 newtons per meter. Give me a second. But the spring itself is negligible, so we don't need to know about this anyway. Cross it out. This is just our extra information, as well as frictional forces. So ignore any frictional forces. What is the max height that the Rubik's Cube can reach? Well, we can start by sketching a little diagram of the spring that Ethan is messing around with for no apparent reason. So this is a spring. Yeah, it's a Rubik's Cube. I'll do my best to render a Rubik's Cube. Oh boy. Rubik's Cube has a mass of 0.3 kg. Hello, let me get it. That's, there you go. 0.3 kg. Spring constant here, which is K, is equal to 2,000 N over M. And what else do we need to know? The vertical displacement of the spring when he presses or compresses down is 0.04 meters of displacement, right? Okay. We can do conservation of energy here to answer this question, right? So energy initial, energy final. So the energy before is equal to the energy after. So E initial is equal to E final. Let's observe the energies in this system. So energy before this Rubik's Cube and this spring, there no potential energy gravitational, because there's like, we'll first off we can call this to be y equals 0. So it's good. I'm not going to draw it, but you can imagine after this Rubik's Cube is released from this compression, it will go up, right? And then the spring will go to equilibrium, which is like 0.04 meters from equilibrium. Wait, this is right. Yeah, Rubik's Cube will go up, get max height. So right now, there's no kinetic energy. Rubik's Cube is not moving, so there's no kinetic energy. It's not just 90 years, so there's no potential energy. There's potential energy spring or elastic because the spring's being compressed here. So for the potential energy elastic, the holy crap, my stylus, give my stylus back. the equation is 1/2 k, my stylus, hello, k delta y squared equals to energy final. And the energy final, you can imagine, I'm not going to draw it out, but the Rubik's Cube will be in the air at max height, and the spring will actually be at equilibrium. So there's going to be no potential energy spring or elastic. There's going to be purely and fully potential energy. So UG is equal to mgh, which is mass times gravity times the height or displacement from y0, this y0. And but oh wait, no. Hold on, I need to, it won't let me control Z. Oh, there we go. And the last value is H, which we are solving for. We are solving for H. So we can isolate H to find our answer. It's gonna be 2000 times 0.4 squared divided by these. And you're gonna have 0.3. Oh, 9.8. And this will give you the height. Oh, this will give you the height. And if you do the calculation, height will equal to 0.54 meters right here. Okay. Emmanuel?
Nice.
All right, number 13, Alan is swinging on a swing. That's a massive 2 kilograms. The swing can swing up to a max vertical displacement of 17 centimeters above its resting position. When Alan swings on the swing set, what is the kinetic energy of the swing at the lowest possible elevation? And we have to keep in mind that Alan's mass is negligible, so we just ignore his mass. And this is good because they don't give us his mass. All right, first off, we can start by doing something pretty natural. Is you see centimeters convert to meters, so 17 centimeters is equal to should be 0.17. That should be 0.17 meters, right? So that's the vertical displacement, right? Is all potential energy where Alan's in the air and just he's not moving. That would be just mgh equal to energy final, which is where he's at the lowest point, where it's purely kinetic energy and there's no potential energy at all. Will be 1/2 mv squared, right? And then m's cancel out, so mass doesn't matter anyway. Wait, no. You want m to stay here. And then you want to, since they're equal, you want to know what the kinetic energy of the swing is. So this entire value, well, there's no point in plugging this in really. You have mgh, you know, m, this is the mass of the swing to be 2 kg, 2 g, we can use a good number, 9.8. Multiply by and height, which we had the vertical displacement, 0.17 meters, 0.17. This will give us the total potential energy and the energy initial, we should calculate to 3.33 joules, right? And then conservation of energy, the energy initial equal energy final. This should be the kinetic energy when it's at this lowest point, swinging down at the lowest point. Okay. Let's say, oh boy, let's say, all right, next question.
All right.
Object 1, object 2, right? This one is mass m, the other one is mass small m, right? You know that mass m is much greater than mass small m. Hercules drops both at the same time at the same height, so the height's the same, the time is the same, right? Which quantity is going to be the quantity is going to have the same change? The only acceleration that will be acting on these two objects is the acceleration, due to gravity, just 9.81 meters per second squared. And then this is a constant acceleration. This acceleration will not change. So these two objects have the same change in which quantity, this acceleration does not change. So no. Since we know the acceleration is constant, there will be a constant change. And we also know, we know except 15, Jumbo. Let's see what Jumbo's got. Jumbo works at a bicycle factory, right? Where let's see. where he is responsible for overseeing the engine that powers the conveyor belt that moves the bicycles in the assembly line. This very engine maintains a constant power, but if the belt's velocity is doubled, what happens to the magnitude of the acceleration? All right. So power, where do we know power? So Newton's second law, force equals ma, F equals ma, force equals mass times acceleration. All right, so what exactly is power? So power is equal to, well, we know power is measured in like watts. And what is watts? Watts is joules per second. We know about joules per second. That is work over time, right? So work over time. We don't know about work. Work is equal to force times displacement over time. What about displacement over time? Displacement over time, well, we've seen this before. Force times velocity. Displacement over time, change velocity. D over T is V, right? A velocity equals D divided by T. I believe that's it. V equals D over T. Wait, no, V. Yeah, so V, yeah. It's right. Power is equal to force times velocity, right? Oh boy. Force times velocity. Power is equal to force times velocity, right? And we know here that the force times velocity, and we know here that, all right, so the power is equal to force times velocity. And we know here from the question that velocity is actually doubled, right? So if P equals FV, well now P equals F2V, right? Oh boy, F2V, right? And then, but then this very engine maintains a constant power. P is a constant value. It's not changing. So when velocity is doubled to 2V, what happens is that the force has to go down in order for this to stay constant. So force now has to be, because this wouldn't be equal. Now power has to be equal to force over 2 times 2V in order for the 2 to cancel out and go back to F times V, right? Since velocity doubled, force needs to be halved. Well, what do we know about force? To bring it back here, force is equal to mass times acceleration. So what does it tell us? Ma. If you substitute ma for force, which is ma over 2. Mass is constant because well, this mass. Well, so mass is constant. Mass is constant. What happens to the magnitude of acceleration? The acceleration will be halved of what it was originally. The acceleration will be halved. So the answer is A. Magnitude of acceleration becomes a quarter what it was? No. A third? No, it's just 2, not 3 or 4. The acceleration remains? No, it does not remain. In order for the power to remain constant, the force has to be halved in order for that 2's to cross out, or cancel out rather, since the velocity is doubled, and we know force is equal to ma. There we go. All right.
Mass M1 is right before colliding with the wrecking ball in mass M2, right? We can solve this easily with the conservation of energy. Energy before is equal to energy after. Energy before, energy after. Well, in the picture of the energy before, it is purely potential energy gravitational. It's not moving. And it tells us it's at rest. Right here, it's at rest. So we know this, okay, UG equal to, and in energy final, it is right before it collides, so it is purely kinetic energy, it is moving. And there's no potential energy, so it's KE, F, right? Well, we know UG is MGH, or to put in terms of the variables or letters the problem gave us, M1, G, and H, but we're not going to use H here since they tell us that this height is actually R, since this is the radius of the quarter circle, or arc-like slope. R here will be the same length from here to here, and does not drop the scale. That's the point, so MGR, and 1GR. And energy is equal to 1/2 mv squared. This is still without M1, so it's M1. And now we want to look for the velocity, or speed, right? So we solve for V. Isolate V squared. V squared will then equal to mgh times 2 all over m1. Well, m crosses out, and we just have V squared is equal to 2gh. Square root of this equals V is equal to the square root of 2gh. So now we got, this is our answer for velocity. And what does the momentum initial is equal to the momentum final? To expand this to m, m1, I think, m1, v1 plus m2, v2 is equal to momentum final. It's going to be collide, and they combine since it is inelastic. What does it say that? It is a inelastic. There we go. Took me a while. m1 plus m2 times v final. We don't know what this v final is. We are currently finding this v final of the collided and combined speed. Okay, so how do we do this? Well, we know that, looking at this, we know that chills on the wrecking ball, right? This M2, this wrecking ball M2, well, chills is, I guess another way of saying it, it's at rest, so, you know, V2 is 0, so this M2 is now moving out, technically at rest, so this is 0, this entire term goes to 0, so now just M1 V1 equal to M1 plus M2 times V2, VF rather. 1 is actually equal to, please note that M1 is equal to M2, so the wrecking balls are actually same in mass, so M1 plus M2 is actually just 2, M1. And times VF. And this is M1 over V1, M1 V1 equals that. What we're looking for VF, just divide by 2M, so you have M1 over times V1 is over 2, M1. So the M1s cancel out, and then you just have V1 is over 2 equal to VF. So it's equal to VF. Right. So now we have our lovely equation, which is well, V1, V1, we solved for an A, and if you guys recall, V1 is actually equal to square root of 2 of 2GR, I believe, yeah, 2GR. So we just substitute in 2GR divided by 2, and that's our answer. So V2 is equal to 2GR, 2GR over 2. You might be tempted to leave the answer in this form as is, but you actually can simplify this even more. So we see 2 here, and we see, wait, it's not V2, that should be F in there. Oh, it's 2, that's VF, by the way. We can actually simplify this further. We know 2 can actually go into square root, but this is equal to square root of 2GR over 4. And square root of 4 is 2, and 2 goes inside the square root symbol, 2 squared, right? 4 is equal to 2 squared, and yeah. So 2 divided by 4 gives us 1/2, so we get square root of GR over 2. So this is our answer for the final VF. Okay. Just transfer into the short track, which is this. Or the air around the wrecking ball. What is the internal energy transfer in this collision, right? So what do we know about C? This is asking for internal energy, right? And internal energy is equal to the amount of energy lost, or amount of kinetic energy lost, excuse me, sorry. We can start by changing kinetic energy. It's equal to kinetic energy final minus the kinetic energy initial. Right? Okay. So, and we actually know these values, right? Can I drop that down? Okay, final. Well, we can, when they are combined, after they collided, so that's going to be 1/2 M1 plus M2, but since they're both equal, it's just going to be 2 M1, so 2 M1, right? Times V squared. Minus kinetic energy initial, they were split up, so M1 plus, wait, hold on, that's not right. It's going to be 1/2, boy, minus 1/2 M1 V1 squared, plus 1/2 and 2v2 squared. Let's close parentheses. Sorry for bad handwriting. Well, this is going to go to 0. Why? Because velocity of M2 before collision is 0. It's not moving at all. It's at rest. So this entire term goes to 0. So now we just have, well, since the 2 cancels out, it's just m v squared minus 1/2 and 1v1 squared. Okay. Well, since we do know what's a v here, v final, we actually solve v final in b, so we just plug it back in. We know v final is actually square root of gr over 2. And since it's v squared, it's quantity squared, and it's m, so you just put m. For the m, sorry. Minus 1/2. This v is the initial. This v here is actually v1. The velocity here we solved in a, so we just plug in what we found in a, or our answer to letter a, which is just square root of 2gr. This is velocity squared, this is quantity squared, right? So if you square this value, you would get to m, takes out square root, we just have gr all over 2. And minus, takes out square root, we just have 2gr all over 2. And then the 2 here, oh wait, you have, well, it'll be m here. I made a mistake, it'll be m here, because m, v squared, I forgot about the m, is m over 2, 1/2 of m is m over 2. So you have, here, m over 2. Hold up, yeah. So this 2, and this 2 denominator cancels out. And then you would be left with a, I'm looking for space to write this, maybe I'll just do it here. Right, and let's actually see what we can cancel on the left side equation. You have mgr over 2. I think actually we should just mgr 2, I think that's it. On the right side, we would actually simplify, you would just have minus, what, just the only thing that cancels out is 2, so you just mgr. So mgr over 2 minus mgr. That's just a simple algebra. It's negative 1/2 m. This is just negative 1/2 mgr. Or m1gr. This answer to C. That's the changing kinetic energy, which will give us turn energy transfer. The E thermal produced by the wrecking ball as they move across this short track is actually going to be equal to the work done by the force of friction. Or rather, it would be, actually, if you think about it, right, it would be the negative work done by which. The work done by friction, right, will be the energy thermal produced, will be just negative work done. Anyway, besides the point, we know work to be equal to the dot product of force dot displacement, right? And using the dot product theorem that you learned pre-calc or whatnot, work is equal to the magnitude of F times the magnitude of D times cosine theta. Theta, cosine theta, theta being the angle between the two vectors, right? the force vector, or the vector force, will be pointing in this direction since it is friction. It is pointing in the opposite direction of movement. The two wrecking balls are moving this way. This is velocity, all right? This is a force vector, so this is friction going in this direction. Displacement, the wrecking balls are moving this direction. It is being displaced in this direction, right? These are the two vectors, right? Now, to find out theta, the angle between the two vectors, you have friction, and you have displacement. What is this angle? Straight line, 180 degrees. Plug 180 into cosine theta. What does that give us? Cosine of 180 is actually equal to -1. So then we just get work is equal to negative force times displacement, right? So now for D, or displacement, it would just be this, which is giving us our variable L. So we replace a D with L. Right, and we just cosine theta, as we explained earlier, cosine 180, that's negative 1. Alright, now the force. What force is being mentioned here? Force of friction. What is force of friction? D, normal force, times coefficient of friction, or mu, right? And then the normal force is equal to force of gravity, and force of gravity is equal to mg, right? Right. But in this scenario, the object we're talking about is the combined object. M1 and 2 combined wrecking ball, M1 and 2, they are combined, they're moving together. So the mass will not just be mg, it will be M1 plus M1, since M1 is equal to M2, M1, M2 will just be 2M1. So the normal force will be 2M1 times G, and force friction will be normal force is normal force, so normal force times coefficient of friction, mu, right? So then plug it in here, we have a mu 2M1G times L times -1. And then we will get negative, we just get -2, sorry, mu mg L, right? -2 mu mg L, yeah, okay. And then we know that this is the work being done by friction, negative work, since it is, this way. Done by friction is negative. And as we mentioned in the beginning, energy thermal is equal to negative work, right? Since work is negative. So this info, work done by friction is work done by friction. We get energy is equal to 2 mu, sorry about that, mu mg L, this mu is M. So that's your answer to D. The thermal energy produced by the wrecking balls M1 as they move M1 and M2 as they move across the short track is 2 mu mg L.
FRQ number 2. A researcher uses a camera and computer software to collect data about a ball as it slides down a curved, frictionless track. It is initially released 1.5 meters above the ground from rest. He documents the following data and tries to analyze it. So here's a table. We're given the time and velocity. Question A. Based on the data, what are the corresponding heights for each data point? List them in order. So we have the equation for conservation of energy, which is K initial plus U initial equals K final plus U final. And VI equals 0. Initial velocity is 0. This becomes, so when initial velocity is 0, this just becomes UI equals KF plus UF. Or KF equals UI minus UF. Now we can represent KF with 1/2 mv squared, set it equal to UI minus UF, which can be represented by mghi minus mghf. Now we can cancel out the 3 m's, and we're left with 1/2 v squared equals ghi minus ghf. Now this equation can be rearranged so that we move all the g's, we factor out the g, and we isolate hf. We get hf equals hi minus v squared over 2g. Now, since we have we know the initial height, and we have velocity, and we know the acceleration due to gravity, we can plug these values in and add a third column to our table for height. So if we just keep this formula in mind here, I'm just going to clear out the area and put the formula to the side so we can find all the values. I'm going to demonstrate for the first 3, and the rest should be self-explanatory. So we have the equation hf equals hi minus v squared over 2g. Now let's start with, well, first of all, let's make our third column. H in meters. Okay. So let's start with the first one. We know our HI is 1.5 meters. So HF should be 1.5 meters minus V squared, which is just 0, over 2G. 2G doesn't matter, it's just 0. So this just becomes 1.5. 0.5. Now, the second value. HF equals initial height, which is just 1.5, minus V squared, or G, which equals 1.5, minus 1.41 squared, which is 1.8. approximately 1.9881 over 2g, which we can just use 10 for, should just be 20. And this should come out to approximately 1.4. Be 1.4. Let's do one more just to make sure. Now, HF equals 1.5, which is our initial height, minus v squared, so this would be 2.45 in this case, which is approximately 6.0025 over 2g, so about 20. And this should give us approximately 1.2 meters. So this process is just repeated for all the following values, and the table should be filled out, and that's how you complete letter A. Now, if we take a look at the table, you'll pretty quickly realize that the greatest change in velocity is between 0 and 0.05 seconds. So the acceleration during this time would be given by A equals Vf minus Vi over t, or over delta t, which would give us 1.41 minus 0 over 0.05, which make that clear that that's a 5. 5, which is equal to 28 meters per second. And that's your answer to question B. Let's see, how would the values change if the ball were replaced by a ball of twice its mass? So we have to look at how mass would affect a situation like this. However, if you know basic physics, you would know that changing the mass does not affect the time spent falling or the velocity of the object. Therefore, a change in mass will not affect the results. So the results are consistent regardless of changes in mass. And that's the answer to question C. And there you have it. That is our answer key for AP Physics 1, Project 3, Work, Energy, and Momentum exam.